Hello, it's Scott Manley here. A few weeks ago, I was at Open Source with a whole bunch of other creators, and immediately afterwards, NASA Ames Research Facility put on a tour for a bunch of cool people who were interested in spaceflight. And so, as part of this, I got to shoot some video in a bunch of cool places behind the scene. And so I want to bring you behind the scenes at NASA's Thermal Protection Materials Lab.
What's your name?
Matthew. And I'm smarter every day, by the way. So.
Oh, yeah. It's a serious lab coat, man.
Scott Manley.
Hello.
Hello.
Oh.
So welcome. We are going to tour the Sensors and TPS Advanced Research Labs. We are part of the Thermal Protection Materials branch here at NASA Ames. The lab that we're going to walk through is the merging of two labs. One used to be the sensor lab. One was the thermal protection materials. We merged, and so now we're Star Labs. The work that we do here, we do research and development. So, for example, the first stop here, it's where the Space Shuttle tile material was invented. Is do R&D to invent and develop materials, increase their technology readiness levels so that they are ready for mainstream use. And then we technology transfer to companies like Canopy, Stratolaunch, SpaceX, Blue Origin. So when they need a thermal protection material, they come to us. We get a Space Act agreement together, they pay us, and then we teach them how to make those materials.
So the majority of US spacecraft that have been flown with heat shields have used material that was developed by NASA Ames. They have the labs to develop the hardware, and they have facilities like the ArcJet so that they can actually test this under re-entry conditions. And so this includes both ablative heat shield material that gets consumed over time and passive material which can be reflown multiple times. And we began this tour in the lab where they figured out how to make the low density, low conductivity tiles that made the Space Shuttle possible.
So within this space, I often say that we should have a bronze plaque because these fiber bins right here, the downdraft table, the V-blender off in the corner, and the casting tower, these are the original equipment that was used to invent the shuttle tiles. And then they were technology transferred out to Lockheed, and they did the mass production for shuttle. And then nowadays, I think Lockheed is also making the back shell tiles for Orion. But these tiles start off with silica fiber, Q fiber, quartz felt, also some of the names it goes by. And I have these bags so I can pass them around and you can feel what the different fibers look like. But it's a mixture of aluminum oxide fiber, silica fiber, the fiber called aluminum borosilicate, and a little bit of silicon carbide powder for emittance so that it's not pure white. So these all get mixed up with some deionized water. They go in the V-blender, and you end up with this sort of runny, wet oatmeal-looking material. That mixture then goes into the casting tower that's right here with the acrylic clear front face on it, and the water gets drawn off the bottom till it's what we call a wet cake. And once we get the water drawn off and we know the cake height, we can calculate the final pressing height to get the density that we desire. So then it gets pressed to that height, the rest of the water gets drawn off, and what we have right here is the result of that process. So this is a dried cake that is now going to go for firing. When it's fired and trimmed, this is what it looks like. All of the equipment here, you can see all the ductwork over your head. That all goes to a very large industrial dust collector outside that collects the dust, so we don't have to wear bunny suits and respirators when we work with it. So everything is dry, no lubricants, no oils anywhere, all gloved hand.
I have scripts to write, videos to edit, and the occasional actual airplane to fly when the weather and the schedule line up. Somewhere in all of that, looking after my own health keeps sliding down the priority list. The old process made it worse. You'd end up in research mode, 20 tabs open, trying to work out who's in network, calling offices that put you on hold and then forget about you. That little bit of phone anxiety for me is enough to make me close the laptop and decide that it can wait. Again and again. And that's why I'm happy to say today's video is sponsored by Zocdoc. Zocdoc is a free website that lets you search and compare local doctors who will take your insurance. They have over 150,000 providers across over 200 specialties in all 50 states. You can read real patient reviews, look at detailed profiles, see the actual open appointment times, and book right there on the spot. Most people get something within 24 to 72 hours. Some people can even get them next day. And video visits are in there too if your calendar is a disaster. It cuts out almost all the busy work, so the "I'll do it later" loop finally breaks. I use it because it gives me back time that I don't have to spare. Taking care of your health just got easier. Head to Zocdoc.com/ScottManley to get started and check that appointment off your to-do list. Link is on the screen and in the description. And thanks to Zocdoc for partnering with us. All right, let's get back to the video.
So this shell rotates and hydraulically mixes the slurry, and as it goes back and forth in that hydraulic mixing, it passes by that intensifier bar that's rotating at about 4,000 RPM, and that chops the fiber. So the amount of chop that you're going to apply to the fibers determines the fiber length, and different fiber lengths, there's a really narrow window to where you can achieve something as low as an 8-pound density tile or scrap. When you go for 17 to 20 pound per cubic foot densities, it's much easier to get because you're pressing them to a higher pressing depth. But on the lower press, for a lighter press, for say 8 and 12 pound densities, they're more challenging to make. So the fibers start off what you had in the bags over there. We take a certain amount of those with deionized water, silicon carbide powder, and it goes in the V blender here. And then this is what it looks like after it's been run for about 17 minutes.
If you ran it longer, it'd get shorter.
Right, it gets shorter and shorter, and the shorter the fibers, the more likely you're only going to make a 20-pound density tile or even greater. And the higher the density, the less effective it is as a TPS. You have a weaker strength through the thickness, stronger through the sides, and its ability to transfer temperature from outer to inner mold line is very limited because the fiber direction is horizontal, and it's about 94% air. So air is not a good conductor. The heat hits those fibers and it radiates out horizontally with the outer surface, and it will maintain the majority of its heat just at the outer surface. So you could have, with one of these tiles with what we call an emittance coating, you could have 2,400 degree outer temperature, and 2 inches away, it's maybe 100 degrees. Over the time we've been doing it, hasn't changed at all. They are right. They are static. It's that effective, and even some of our space partners right now, I won't name names, came to us and they wanted something that was better, and we told them this is still state of the art for reusable. They went off to try to make their own, and they came back a few years later and said we need to do a tech transfer because we need to know how to make what you're making. So it is still state of the art. Whether there are a couple of different recipe families. There's AETB, which is the one here. There's FRCI, which is fiber reinforced composite. It has a different mix of the fibers. And then there's the Lockheed LI Industry ones, which are pure silica with silicon carbide. But those are pretty much the three families, and within those densities from 8 pound per cubic foot to about 20 pound per cubic foot. If you look at this would be the top surface that has the 12 on it. You don't really see a fiber direction. Sure. But if you look at the side, you can see the fiber lay is horizontal.
So was it compressed in this direction?
It was compressed in this direction. So when the fiber goes in this casting tower, and the water is drawn off the bottom, the fibers will settle on the bottom and they will lay horizontally. If you draw it off at the right rate, if you try to go too fast, you don't get the right fiber lay. And so here's a bucket if you wanted to give it a stir to see what the large mix looks like. It's
really high tech.
It is super high tech. I mean,
This is really not what I expected.
No?
that one we can't touch.
Okay, I'm wondering.
I can put a glove on and I can rub a little off the corner if you want to see how this in its current state it is unfired, so it's very friable.
Okay, so this is what comes out of that
right.
mold.
That's a green
right.
billet. It has not been fired. When it gets fired and cut and cleaned up, that's what it looks like.
That's what, yeah. And then this will be further cut to the particular tile
Yes.
shape before,
Yes.
yeah.
And so the room that we're in here, that we call this our roughing room.
Yeah.
So anything that's going to be cut from this gets cut into its rough stock, and then it's going to go to our machine room, which will be in a little while.
Yeah.
These would be reusable materials for multiple reuses as a thermal protection system. But they're not quite ready yet. They are still slightly off-white. So you can see sort of the grayish appearance of the slurry that's in the beaker right here. That's because of the silicon carbide powder that's part of the mix. So when you're out on orbit, white is reflective, so it's a good insulator for solar energy. But when you're re-entering, white is not good because it's going to melt. So you need something that's good for the convective energy from re-entry. And I'll show you what that is in a little bit. So if you try to re-enter with this bare tile, you'll get a little bit of the way into your re-entry, and then temperatures are going to increase, and then it's just going to melt, and the glass is going to flow like water.
For like Orion, it's the reverse. The black TPS is on the back shell now, and you've got the ablative on the.
So we do have an ablator here. This, since you mentioned it, we got so sidetracked on this, I overlooked. This is a block of flight Avocet for Artemis, probably about half of a median family home in the Silicon Valley value. This is a piece of block Avocet that's just a cut-off trimmed scrap, so I can pass this around, you can handle this. So this is the ablator. We don't make the ablators here, typically, at least for Avocet. That's made by Lockheed, and also formerly by Textron.
Is that the new formulation that's more porous?
I am not sure which one you're holding right now.
Okay.
This one is the panel.
Okay.
So one of my favorite things I saw open source were these heat shield samples from Artemis 1 and Artemis 2 on the bottom, showing the difference between the different re-entry plans. And they were able to extract these thanks to Bart and Lisa.
This is a tool after Artemis 1 came back and there were a lot of anomalies in the heat shield. We needed to secure as much of that heat shield for analysis as possible, and no tools existed to do that. So this is my brainchild. This is Bart. This is the block Avocet removal tool.
The what?
It's right here, the block Avocet removal tool. So we have Bart here. This is Bart that's partially set up just for in-house testing and for training for disassembly, kind of the R&R that we do in between uses. And this was used on Artemis 1. Each of these numbers that's written on here is the block number, the sample number that was extracted with this particular saw. So this is Bart in action.
You made it.
These are by size. So Bart was the first for 8x14. Lisa was 5x6. And there were some little channel coupons, and so I had a Maggie all ready to go. So.
In the next room was a furnace, and it was time for the famous hot potato demonstration.
Oh, that's a dramatic intro.
Oh, there's the thumbnail.
If you come closer, it's also nice in the wintertime.
Yeah.
Yeah.
Okay, so you can see that is still glowing inside. And so we can pick that up. That's 2,000 degrees. Gets a little bit warm, so you have to kind of dance it back and forth a little bit. But you get a good roughly 30 seconds out of that where you can still see it glowing.
So the reason why you can pick up these heat shield tiles straight out of the oven is because they are so low thermal conductivity. As soon as they come out of the oven, the outer layers cool just enough that you can touch them, but then the heat from the inside doesn't flow out quickly enough to burn your skin. And of course you can still see it red hot. That's because it's getting rid of heat via black body radiation. And that's the reason why you end up swapping the block from one hand to the other, because of the heat radiating out of this, rather than the heat conducting through your fingers, because there's basically no thermal conductivity. Now, many of us already knew this, and we also knew that there was a second tile in the furnace. And so the inevitable question was, could one of us try it?
I can't have non-NASA personnel.
Oh, okay, great. Perfect. What if that person's wearing a Nomex suit?
If you're wearing a Nomex suit, or even though you're probably okay.
That was my point.
Try to grab it up high so it stays as hot as possible.
You tell me when.
You can see, how about I'll hand it to you.
Yeah. Touch the cube.
Yep, right by the corners.
Well, that's wild. Oh, yep, your fingers get hot. Can you stand next to me?
Yes.
Yeah. There we go. Do you just do this for fun sometimes?
No, I would in the wintertime because it feels nice and warm.
It's pretty slick. And you're saying the inside is still like 2,000 degrees?
Yes, if you could cut that, the center of it is still 2,000 degrees.
Wow.
Get a really close one.
Good.
That's thumbnail.
Right there. How's that? You see it? Yep, that's getting hot.
Right, you can't really see it glowing orange anymore, but you can feel the heat for sure.
Oh, you can. Well, I can feel the heat radiating onto my hand,
Mm-hmm.
like my parts that aren't touching it, like here. That's really,
Absolutely.
yeah.
So after the raw material has been manufactured, fired, and cut to the right shape, they need to apply special coatings.
Yeah. That'll be the worst ice cream sandwich you've ever taken a bite out of. So this is the coatings lab. So I have two examples. So trying to keep things sort of in line with Artemis. What we have is the RCG coating, which is a coating because it sits on top of the tile. It does not penetrate. And then we have the Tuffy surface treatment, which penetrates. I'm not sure if there's Tuffy on the back shell of Orion. Is there? Okay. Okay. Yeah. So normally the place where this would have been probably used first on a vehicle is in the engine bay of the orbiter when it would launch and the concrete would spall off, come back and hit the vehicle. This protects it. So I'll pass this around in a moment. You can touch it. So the process is kind of similar for these two. They start off with what's called a borosilicate glass powder. So it's just a white, really fine glass powder. Passes around. You can kind of just kind of rub it between your fingers. You can feel the granular nature of it. And just imagine as you're rolling that, the particle size that you're feeling is massive for what we want to do. We need to get this down much farther below 2 microns. And so what we do is we take the glass powder. This is tetraboron silicide. There's a small amount in here because the last time it was made, it was $16,000 a kilogram. And by today's pricing, it's probably going to be at least double that. So RCG is going to be borosilicate glass powder, SiB4. They get mixed in the ball mill right here, which is a aluminum oxide jar with aluminum oxide media. It tumbles, and then the impact energy from the media, it reduces the particle size on the RCG a little bit, but mostly what it's doing is it's mixing it. On Tuffy, we actually have to get it down to that sub 4 micron. So we mix those powders in the ball jar, and if we're using the ball jar ball mill process, it takes about a week and a half of running 24/7 to get the particle size where we want it. Well, there's this other device that's called an attritor, and what it uses is these 5 millimeter zirconium oxide spheres. They get poured into this grinding tank, and they get stirred by this agitator assembly. And so there's a lot more energy and a lot more impacts because of the smaller spheres. And so we can do with the attritor in about 90 minutes what it takes a week and a half to do in the ball jar. And we get a more pure coating. So you see the weights on the jar for the weight of the jar, the media, and the lid. That's the starting weight. When we're finished, we weigh them again to find out how much aluminum oxide was added to the coating, because it's an undesirable addition to the coating. Not quite a contaminant, but it's undesirable. It lowers the melting temp. And the attritor, we get a little bit of the Tefzil lining, but that sublimates when we fire the coating and sinter it. And then what's left is a little bit of the, for each 90-minute run, we expend about the volume of 1 sphere of the zirconium oxide. And that's much more beneficial to the coating than the alumina is.
So the material's so fine it can penetrate in. Is that
Yes.
what I'm hearing?
Right. So the sub 4 micron, it allows the coating to penetrate.
And it's just you paint that on. How do you apply
we
that?
spray it. So that's what I was just going to say next. We have the spray booths that are behind you here, and we use automotive type spray equipment and artist airbrushes. And so the pressure and the spray, you don't spray it like a paint. You get the nozzle right up on the edge of the tile, and so you're blowing the alcohol and the coating.
And it just gets carried through the tiny porous.
Right.
Yeah.
And then we spray this in. We don't want the uniform density of the Tuffy. We want the majority, since it adds a lot of weight to the tile. We want the majority out here where it can do the most good. So it's sprayed in 4 applications typically, and each one is a smaller percentage of the previous, so that you end up, if you look at this when I pass it around, you can see that the depth is not terribly densified with Tuffy, but that outer layer is much more densified.
Yeah. So it's basically making the entire matrix stronger.
Yes,
as
the
it's-
matrix
yeah.
is stronger at the outer surface.
Rather than just being painted on the outside, which is the
Right.
older material.
And so this is the RCG. The standard RCG is nice and jet gloss black like this. This is a modified RCG for something else, but it's a sample I have that is cut and gouged, so you can see that it's about 12 thousandths of an inch thick once it's fired. And so it's this is the protection. So this RCG coating is what keeps the heat right out here at the outer surface, and then it radiates the heat back away because of its emittance.
So does it stops like the plasma actually flowing through it?
Yes.
Yeah.
Yeah, so this also seals the outer surface of the tile, as does Tuffy. It doesn't seal it against water. As a matter of fact, first time I saw what they do for waterproofing, I was mortified because when we do test articles here and we do other things for other flight projects, we're expected to have something that looks pristine like this. Well, when something like this is mounted on the shuttle, the first thing they do is take a syringe that's blunt and they pound it through that coating and inject waterproofing. So this tile would have probably a punch mark here and one here that have cracks that radiate from each of those punch marks.
What?
Exactly. If you ever make it to the Air and Space in Virginia and you're able to walk down the underside of the Discovery, you can see all these places on the tile where there's a paint circle around them to identify where those punches are, and you'll see they're all over the acreage of the shuttle, and that's where their first waterproofing is injected with a syringe.
So would you have to reapply the water?
Yes, waterproofing is reapplied.
Yeah.
That's why they're
it bakes
then
out
marked.
during entry.
Yes,
Yeah.
that's why they are then marked so that they can locate the same hole and not have to punch multiples.
Yeah.
But you can take this. Just please, you can see 3 places where people have tested it with their thumbnail. Please don't alter these in any way or try to shed material off it. But you can feel it to see how light they are, and so you can.
Ooh, he's counted the thumbnail marks.
I
He's
know.
gonna know.
Yeah, I know how many
Yeah.
they are, and I've seen all of your hands, so I can.
Yeah, my fingerprints are on this.
On the way out, we're
CSI
gonna.
Ames.
Yeah, it is actually not. It is not very. It's not really adhered. That coating, when it's fired, it shrinks, and so it is held onto the tile by the compression of. Right. So if you try to spray just the top surface, it will peel, because it shrinks when it's sintered. It will peel off. So it has to wrap around the side of the tile at least about what you have there is about a ½ inch or a centimeter. It has to wrap around at least that far, or it will peel off.
But yeah, this is tougher, right? The acronym is a joke in the fact that it is tougher and stronger because it goes all the way through.
Absolutely. It is humorous, but it does work.
Yeah. So it's interesting to see. These particles must have been shot in there by the pressure, I'm guessing, and then it just creates a trace.
Interesting.
So they're pushed by the pressure from the airbrush. They are also in alcohol. So this, when it's sprayed, it's 25% solids in alcohol. And the rollers you see around the room, these have different coatings on them that are on the roller to stay in suspension. If the power goes out or any of these things ever stop rolling, the powders settle in the bottom of the jar, the alcohol rises to the surface, and you can never disperse this again to make it usable. So if we have a power outage on the weekend and come in Monday, everything has to get thrown out and redone.
So this is basically how it's stored. It's not. Yeah.
They are not stored. These are just here for historical samples and in case we ever need to take something for analysis. But they do not get stored like this because this is no longer useful for anything.
So next up was the place where they were machining the tiles into shape. And in this case, they were primarily working with the Avocet ablative material. They were building sensor plugs that would go into a heat shield, but they would also carry sensors through to the surface so that they could analyze things. Unfortunately, I didn't get much footage from this, so imagine things.
Okay, so this is our main machine room. And then I heard you point out it's a Haas machine, so American made. That's important to us. It is also well within the level of precision we need for thermal protection materials. So
He's your machiner guy, right?
yeah. So we do not need Mazak or anything really impressive because everything we do, you can see it's held down by vacuum. This plug is held down with a vise because it's on a mandrel. But these materials, if you try to hold them mechanically, you will damage them. So we have a vacuum hold down system that holds them for machining. It's adjustable, so it's a low vacuum, high flow because they're so porous. And as you can also see, no coolants. Everything is 100% dry. And so there's, again, each machine has a stovepipe that goes up and out to a large industrial dust collector. You can see the snorkel right here. It's moved away right now so you can see the drilling happening. But normally that snorkel is aimed right at the cutter, and so the cutter will throw the dust off and it goes right in the dust collection. So it's all completely dry, no oils. And so this is a plug mock-up. So whenever we do instrumentation like we did for Artemis, we machine a blank plug down here. That plug goes upstairs. It gets thermocouple wires and different insulator materials put on it to insulate the wires, and then it leaves here and goes for installation on Artemis.
So when you're machining this, you got to figure out just how fast you can machine it to stop it getting too hot, because it is TPS. You don't want it to change properties, right?
That's true, but they don't actually generate very much heat.
Okay.
Even dry. If we do have an issue, this pipe right here is plumbed to a cold air nozzle.
Yeah.
And so we'll where is it here? I don't know where it's mounted, but there is a cold air nozzle.
Okay.
That will blow cold air on the part.
And it's just air. It's not even like nitrogen.
Just
or
air.
anything. Okay.
And clean air.
Yeah. Obviously.
And the final stop on the tour would be this lab, where one of the things they would do is they would analyze materials that had gone through tests on the ground, or even after test flights to space.
This is Artemis flown. I don't think anybody in public has seen these yet. So
Oh, will I not be able to share it?
You get to be the first group. So I will wait to talk about these until the group is up.
I'm just going to get the close-ups, that's all.
Certainly.
And so I'm pretty sure I recognized what these were right away, and it looks like they'd actually flown. And they are the compression pads which are used to support the weight of the capsule against the service module. Each of these can handle something like 25 tons of load, and they're donut shaped because up the middle there is the explosive bolt system which is used to hold the spacecraft on the service module.
He'll probably tell you some stuff in a minute, but I'm still going to hog the camera. So these are pressure pads for Orion. It was a material that was invented here. It's called 3D mat, and it is a really cool, this is something that has been handled, so I don't know if you want to pass this around and hold it. It's kind of heavy. This is a three-dimensional quartz fiber weave, so it has fibers in X, Y, and Z directions, makes a really interesting structure, and then it is impregnated or infused under pressure with a cyanide ester resin, and when that is cured, you get a pressure pad. And this had to come about because other pressure pad materials don't perform similarly enough to the Avocet material to work in harmony with the materials. So this is actually a compression pad that can handle insane compressive loads, but also function as an ablator next to the Avocet. So it's more in family with Avocet than other pressure pad materials would have been. So this is a prototype. And then I have here, when it was in development, we did some instrumented test articles. So this is a instrumented plug, kind of like the one you saw running on the machine downstairs. And I can pass this around if you want to look at it. At the end of each of the channels down the side, there's a 10,000ths hole that goes all the way through it. And we have tried to get other entities to manufacture things like this, also out of older pressure pad material types like the carbon phenolic, and they keep coming back to us unfinished. And so far, to my knowledge, we're the only ones that can make a plug like these.
So these pads are how the spacecraft is secured to the service module,
yes,
right?
There are 4 of those, and that's how it is secured for launch. And then through the center, there is an explosive bolt that's about probably 1.25 inches or so diameter, and then there's an RTV gasket around to that. And so when it separates, all 4 of those explosive bolts are detonated, and makes it actually a really cool, clean break. Looks like I've seen them when it came back, and it looks like they are beautifully machined the way that they.
So the bolt is pulling down onto the service module,
yes,
and that is reacting against that pressure. And that's why it needs to be stronger than the other TPS.
That and during the launch, when all the
handling the loads.
exactly saddling the loads of Artemis 5 meter.
Yeah, and the vibration.
And I don't know what Artemis weighs. I should probably have that number, but when you have that with the G load,
right.
These things can handle way more than that.
Why do they have to have great thermal properties if they're underneath the...
It doesn't have to have great thermal properties, but it's better if it can function sort of in family, in concert with the type of heat shield you're using. So if the Avocet is recessing around a heat shield, around a compression pad that's not, you're going to get some different airflows around that compression pad that might accelerate the ablation at that region right around it.
So these flown entities, or whatever, these flown pieces.
This is an actual Artemis one,
Yeah.
Compression pad, bolt, and adhesive removed, and it's been sectioned and sampled for analysis.
But the fact that it's going down, that shows us that the bolt was recessing faster than the material around it.
Well, this is going to show you that there was greater heat in this region.
Yeah.
Most likely because of the RTV gasket. Sometimes they will protrude a little bit. We call that fencing, and that creates turbulent flow around that fence. And then you also have probably additional heating here from the bolt.
I see. Yeah.
So that's why you see that pattern where out at the heat shield, you have a char layer that probably matches pretty closely what the heat shield had. And if you look at some of the pictures you can see online, you'll see that around the heat shield is not a nice, clean, smooth dish shape all the way across. There are little ramps where each of the compression pads are. So Lisa does not have a blade. We can get her to reciprocate and make some noise, but she doesn't have a blade mounted. So this is the benchtop article we made to prove out the function of Bart and Lisa. This one was last minute because somebody thought, well, if it cuts Avocet, are you sure it's going to extract a sample where there's an instrumented plug? So we had this one made with the aluminum oxide insulators penetrating so we could cut across, and you can't even feel it when you're cutting it. It severs right through them without issue. So we had a few of these made. We use them for proofing the process and for in-house testing.
What does LISA stand for?
LISA is the lesser incising saw for Avocet. So
You see the smirk on his face
so-
when he said that?
yeah, I can't not do that. So Bart is the block Avocet removal tool. Lisa is the lesser incising saw for Avocet. Then down here we have some of the DFI instrumentation. This is a shock vibe test article for the spectrometer. How many were on Artemis 3? One.
Just
One spectrometer. Then we have heat flux, and then we have instrumented plugs. So this is a plug is the plug something we can pass around?
Yes, it is.
Oh, okay. So this is an Avocet plug. This is a ArcJet test article plug, similar to what would have been on Artemis. It is Avocet material. Normally this little void up here is going to be filled in with ceramic adhesive, and there would be a different epoxy to tack them in at the back face, but that's a ArcJet test article for Artemis.
So I think this is something that's often overlooked, that the heat shields aren't just monolithic sheets of material. First, for a start, you have to have those bolts that go through to hold the capsule on, but you also have this instrumentation that is not only detecting the state of the heat shield, but in some places there are literal holes through the shield so that you can use optical sensors to look at the shock wave just outside, measure the temperature, measure the spectroscopy so you can see what kind of materials are being lost from the front of the shield.
So wait, is that a spectrometer that goes through the heat shield and looks at the stagnation layer or something?
Yes.
That's right. So, per your point, it does
I'm
have.
going to let go, so it's all yours.
Sounds good. It has an aperture open so that it can view the radiation coming from the shock.
And
So
what do
in
you
that
fill
hole-
that with?
Nothing.
Nothing? It's just,
So-
it's literally a hole?
The back half of the hole, here's a cross section, is filled with sapphire rod. So
Didn't
that's
more
our,
like it. Okay.
our optical path, and then it's surrounded by an alumina insulator, and then that goes into all the mounting stuff that you see on the back. And all we've done here is created the system for the aperture and mounting that optical sapphire in the heat shield. And then these fiber optic cables connect to the spectrometer itself, which is elsewhere in the
Right.
vehicle.
And then I guess the radiometer is very similar because it also point through the heat shield, right?
Yes, they have a larger frontal area, and so there is the copper, and then there are a few different types of windows and coatings that we have on the radiometers. So whereas the spectrometer, the optical subassembly is recessed below the outer mold line, and as you see, like it looks like just a little hole.
Yep.
When these are mounted, you see a nice little copper circle with either a window or a black emissivity coating.
Yeah, okay.
Right there, flush with the surface.
And then the recession sensor, it just burns back and it tells you how long it is.
Exactly right. So it's just a blind hole from the inside. The thought is once the surface recesses enough that that blind hole has the surface over it removed, you can see again the light from the shock and a simple photodiode.
Oh, it's just a photodiode looking up a hole.
Again, that's sort of on the far end. I think Tomo
Yeah.
finished that. Tomo, is it measured by a photodiode for the ORS? Yes, we got
Yeah.
confirmation on that.
But these are all basically holes through the heat shields,
through the
which
heat
generally
shield.
we don't talk about.
No.
No one wants holes in their heat shield.
And we poked dozens of them through.
But we're doing it for science.
So why do we do it? Yeah, exactly. We do it for science. We do it to better understand
Yeah.
the connections between the trajectory we flew the aerothermodynamic environment that created, and then the response that created in the material.
Yeah.
And so improving that modeling helps us carry less margin with greater confidence on future missions.
So you don't need to fly with the holes in the heat shield anymore.
Actually, NASA requires that we include instrumentation on all of them, so we're going to continue to do the science and improve, but what it lets us do is it lets us get away with a thinner and therefore less massive
Oh, so a
heat
less
shield.
safe heat shield.
So we can bring up a fifth.
You're hearing this, right?
Safe.
That's what the numbers tell us.
Mass is margin.
That's right,
So I learned this
exactly.
recently, the less mass your spacecraft has, the more margin you have in launch availability. And the more
Yes.
launch availability you have, you reduce overall risk.
Sure.
Actually, I have a dumb question.
Yeah.
This is not my area of expertise. So we
Mine
put,
either.
We put holes in the heat shield,
Yeah.
right? But the heat doesn't conduct through that, right? Because
That's
you're not,
right.
because it's going to hit it and it's going to build up pressure and it's going to flow around.
It's a blind hole is not in and of itself a death knell. It's not in and of
Whoa,
itself.
let's work on our terminology.
Yeah, I thought long and hard and couldn't come up with anything else.
Like, I
A
don't
blind
think,
hole is not.
like heat's not going to conduct through there, right? I mean, it's going to
No.
be air or your
Yes.
air is coming through and it's compressing and it's
Exactly.
building a flare and it's going around.
Yes.
So
you can get away
You can have
with-
your temperature sensors, your probes, your sensors.
Exactly.
We need the more data, the better data.
Yeah. But we care deeply about sealing them and making sure that they remain blind holes.
Yep.
Don't get
Make total
close.
sense.
Yeah.
Another fabulous thing they brought out for show and tell was something that had gone through a lot of testing in the ArcJet facility, and when that test was over, NASA proclaimed that the Artemis heat shield problem had been solved. And this is the image showing two pieces of the Avocet side by side, but the one in the bottom was the current formulation, the one at the top was a more porous formulation which would reduce gas buildup. As I was watching one of the scientists explain this particular piece, I realised that I had in fact seen it before.
So this is the one that we see in all the PowerPoints on the heat shields. This is the actual thing.
And you can tell, and you can tell that's kind of like a time
Yeah.
snapshot. That's how it started. So the top and the bottom, you see the bottom didn't look good from the very beginning. That's how it progressed.
Yeah.
Had a lot of popcorn, we call it.
Right.
Little pieces start flying off, and eventually, like the bigger pieces came off on the corners. Yeah.
But this was
But this material has not flown yet, so they'll be flying on Artemis 3.
Artemis 3, where you don't
Artemis
really
3.
need the extra performance because it's orbital.
No, it actually could be worse.
Oh, okay.
Because
Well,
the
good.
heating is lower. Actually, the material cracks more at lower heating. That's the weird
okay.
one. Yeah. So.
So again, it's always cool to see stuff that you've only seen in pictures in person. So this is what happened to the material after it was placed in the ArcJet facility, which drives megawatts of plasma over the surface, and on top of that adds a whole bunch of laser power to replicate the conditions seen during lunar re-entry. And so we got to the last stop on the tour, which would be amazing for anyone that hadn't already gone to Open Source and seen these things sitting out in the open.
So for final stop, we have two panels that were extracted from Artemis 1 using BART. And for proof, my name's right there on the Traveler.
Okay.
So this is one that had a gap that ran across it and also experienced char liberation. I'll have to show these in the tubs because we can't pick them up and take them out. But so this is the Artemis 1 that has the RTV gap in between two separate panels, and these are the char liberation sites on this particular sample.
Okay.
So OCOM thought this would be a really cool tour ender, and then I found out half of everybody's going to be at open source, so then kind of
It was.
undermined that a
It was the
little bit.
best thing I saw there.
This is ideally what you want to see.
Yeah. And you can see the direction the air was flowing across that, right?
Yes, it's really cool. I don't know if there are any that are posted online, but some of the photos that we see, you can see all of the flow paths all around the heat shield, and it's pretty interesting.
My favorite photo was the one they took from underneath when it was still in the water.
Mm-hmm.
Yeah. That's like a piece of art.
That's only Artemis. If we touched on everything, I could keep you here for the majority of a day. So I feel like it was a short tour, but it was probably one of the best tour, most enjoyable groups that I've taken through. So thank you all.
And so that is the end of the tour. Thanks to Matt and everyone else at the lab for hosting us and answering our dumb questions. And thanks to everyone else on the tour for asking the dumb questions so that I could pretend I was smart. And of course, thanks to NASA in general for putting on this tour. I'm Scott Manley. Fly safe.